Okay, so my lecture will not be actually a lecture. It's planned as some introduction for maybe for younger students to the simulation software, and as a hands-on tutorial with the Jan4. So probably many of you already have experience with it. So I apologize. Okay, and let's start with the motivation why we have simulation. How do we actually use it in experimental physics? And basically, experimental physics is all about testing hypotheses. Here, is it actually visible? Mm-hmm. Yeah, the slides are dark. Yes, but this is a legendary experiment by Galileo where he dropped the different objects, the cannonball and the rifle bullet of the Pisa Tower. And according to Aristotle's hypothesis, the speed of the object should be proportional to its mass. So they would fall at different times, and according to Galilei, they should fall at the same time. And here is a nice painting with the Grand Duke observing Galilei performing this experiment and watching with big interest. Well, and I presume that this is supposed to be quite a simple test. If delta t, difference between the falling time of this object is 0, then Galilei is right. If it's not 0, but some value predicted by Aristotle's hypothesis, so the numbers are arbitrary. I didn't make any calculations for Pisa Tower in Aristotle's case. Then Aristotle is right. And yes, the Grand Duke is watching. Probably he's a funding agency and big boss. And then this happens. So the measured value is not here and not here. Of course, because the real world is a little bit more complicated, there are a lot of sources of systematic uncertainties. The height of the tower is not known precisely. The wind goes in some direction, moon phases, etc. So in order to interpret this, we need to we need to change our predictions from our hypothesis. Of course, we need something like this when we take into account all the real world's, let's say, imperfections and hidden factors. We get the distributions. So for both hypotheses, they do not predict one single value. They predict a range. And these distributions, probability distributions, are what we actually need to interpret the result. So in this measurement, we can see that the likelihood of having this value in the hypothesis H1 is higher than in hypothesis H0. So this probably is a hint that Aristotle is not right. But actually, so this example is like ironical example because as far as I know, this experiment never happened in reality, so it was a thought experiment. But some other people actually did this experiment around that time, and about half of these checks were in favor of Aristotle's hypothesis. So interpretation of the data is really important. So how do we build this probability functions? So this is called the likelihood function, and so we're measuring observable x, and the likelihood function is the probability to observe this observable value under the given hypothesis which we consider. Usually, of course, we need to take into account all the unobservable factors, everything that is not x, and the probability function, the probability density under our hypothesis is multivariate. And of all these unobservable parameters, they're called nuisance parameters, we need to integrate. So this, the more degrees of freedom you have, the more of this news you have, the bigger your integral fold is becoming. So this huge integration, if done numerically, can be quite difficult, quite cumbersome. So for this, often the Monte Carlo method is used. So it's statistical method for integral calculation. And in contrast to, so if we have this threefold integral, and we calculate it numerically as a sum of small values, this number of samples will become very large very soon, depending on our parameter space. But Monte Carlo is one of the methods which allows you to reduce number of samples. And in Monte Carlo method, these samples are chosen randomly, and they are used to estimate integral. Okay, so for the example, there is an old joke: how do you find Lenin square? I don't know how to correctly translate it. And an uneducated person will say that you multiply the width by the height, but educated says that you should take an integral. And yes, one of the variants that you calculate the integral on the Lenin function, which can be found in the complete collection of Lenin's works. So here this is Lenin, one of the biggest statues. It's located in Dubna. And we can define the Lenin function to be 0 if the point is outside Lenin, and 1 if it's inside. And the Monte Carlo method looks something like this. So you can estimate the Lenin area as a fraction of the total simulation area. And this methods, you see, the more samples we get, the better our precision becomes. Okay, so Monte Carlo also useful not only for integration, but basically each sample which we're using for estimating our integral is a point in this parameter space X and all this news. And if these parameters are corresponding to some random processes, so each of these points is a realization of random probability. So this is like a random event, possible event, which we can observe in our detector. And the integrand of our likelihood function becomes a probability density function for this. And if we sample it correctly, this we get this complicated simulated events which can be used for many things. So for tuning algorithms, you get to work on the algorithms on event by event basis, and also some machine learning algorithms. So this is very useful feature, and in many cases the simulation is considered to be the main goal of simulation is considered to be this. Okay, so in particle physics, usually the typical pipeline for Monte Carlo simulation is quite complex. So you have your physics, you have your detector, you have all the electronics. You need to produce the whole chain from initial thing you want to study down to the observable data, to the digits in your data acquisition system. So it can be split into three layers, let's say. So the first is generation of the primary particles, like what exactly you want to study. If you're studying astrophysical neutrinos, so this is the simulation of the astrophysical neutrino source, its distributions, etc., and you sample them. And so this is what you get. This defines the physics in question, and usually it's can be neutrino generators, cosmic ray generators, and this is usually these are general packages which can be used in other experiments as well. Then you have your primaries in your geometry, and we need to take into account all the possible outcomes of random processes happening there, and this is like common physics, let's say. We need to take into account all the processes which happen there, and it includes detailed description of the detector and materials, and this is usually done with packages like Giant4 or Fluka, and they are a pretty general purpose. So we will talk about Giant later. And the next layer would be the simulation of actual data acquisition. So how do we get from these particles to what we see in the experiment? And this is usually highly experiment specific. It's, let's say, not portable, and each experiment defines them to its own. So this transforms the Monte Carlo truth information into the format of real experimental data. Okay, so now we will consider out of these three layers the middle layer, because it's the most general, and it's the topic of this tutorial, actually. So meet Giant4. This is the website, and Giant stands for geometry and tracking. 4 is the version number. There were 3 Giants before it, and 4 is the current version. And Giant4 is as it's called by the developers. It is a toolkit for Monte Carlo simulation of the particle propagation in matter. It is an open source package. It's developed by international collaboration based in CERN mostly. And this, what is important for us as users in the next tutorial, it's written in C++ with the really heavy usage of object-oriented programming paradigm. So some part of this introduction will be dedicated to this object-oriented programming, because you cannot make anything in Giant without stepping on, without creating a class, an object. Also, Giant, if I'm not mistaken, in French it means a giant, and it's also a very fitting name for this package, because it's really big and sometimes can be intimidating for new users. It has, of course, you have geometry definition, you have physics description. There is a lot of visualization tools, special user interface command system, special data serialization, memory management, and all that. For each of this, you have like dozens and dozens of new classes. Every one of them is unique. So be not afraid. We will use 2 main sources. So there's the official documentation here, and there's also a very useful thing, class index. I wonder, will it work? Bum. no. Just to show the, yeah, maybe we'll look at the class index later. So, but this would be the most useful for us today, because each time we meet a new class, we will have to look there and understand what is it about and what is our obligations to this class, what we need to implement. So a side note, Jant is sometimes called a framework, but the developers call it Toolkit, and the difference is actually the framework usually defines your main function by itself, and user can only implement some of the steps which are being called by the framework. So it tells you, you have this function, you have freedom to define it as you want, and I will call it at the proper moment. So it's called, in programming, called Hollywood principle, don't call us, we call you. Toolkit is a library, and library is good because you have shelves of books and you are free to choose the ones which you need. And this is how, I think this is how it's supposed to be with Jant. So it defines all the classes and functions which user can call, but user writes the main function, user defines how it interacts with the users, with outside world, and decides which part of all functional should be taken. So for us as new users, it means that yes, we as users decide which part of the library to use. We don't have to learn everything. So if you can run it, this is already good. If you need something else, you just watch for some other implementations and use it as well. Take another book from the library. And also, that means that there are usually several ways to do the same thing. This is how it is in Jant. So it also means that we don't have to use all of them. If we can make any shortcuts, this is fine. Okay, that said, still Jant defines the main event loop, and the flow of the simulation can be so it can be used can be viewed as a framework, because you actually have the functions which will be called by this event loop, and we will use them. And since it's written in C++, and this noble language is not as popular among students now as it used to be, we will use the Python bindings. So one of the available Python bindings is this Jant4 PyBind package. So the plus signs, the benefits of this is it's very easy to install. You just make pip install Jant4 PyBind. So probably if you already downloaded the Docker container, so you will have it there. Or you could have installed it locally. I also showed the instructions. They were in the link. So it comes with a precompiled Jant4, so you don't need to build it from source, and also downloads the data files, which is about 2 GB, and this is the main part of the space of this Docker container. Okay, but important limitations that this binding is not complete. So not all C++ functions and classes were exposed as a Python interface. So there is a lot of advanced methods and classes are not available. And yes, another thing, you might encounter problems. Jan4 uses its own memory management. So it has a garbage collector. It has its own memory allocation. It has garbage collection. And Python also has a garbage collection. So whenever you create like a particle or a vertex in Python and pass it to Jan4, it gets deleted in Python, and it gets deleted by Jan4, and they like can crash. So this is a thing to watch out. However, for the simple cases and for introduction like this, this is very, very good choice, I think. Okay, so for object-oriented programming. Objects is just a specific variable in memory. It's a part of, it's some bytes in memory which have a type assigned to them. So here in this example, this variable s points to memory and it has a type of rectangle, and this is an object. And class is this type of of the object. The type means defining what is inside the object. So it's in class it's called attributes, the variables inside the class, and methods, the functions inside the class. So it's what you can actually do with it. So it's nothing fancy. But very convenient thing to do. So I'm just saying this because many students are like afraid of working with classes, and they're still making everything in functions and functions. Classes are cool, they're free, and very, very useful. The constructor is one method, specific method. In Python, it's called with this underscore, double underscore need. And this is method that describes how this object is initialized, is created. So here we define this class rectangle. This width and height is attributes, and area is a method which calculates the area. And then we have also the constructor, which is also a method. Then inheritance. So it's a way of creating a new class, so defining a new type. Based on the existing type. So this new class called child class is an extension of the parent class. So it gets everything, inherits all the attributes and all the methods of the parent class. So inheritance is good. You don't have to re-implement everything, but the child class can override the inherited methods and also define its own, of course, etc. So in this example, we have this rectangle class, and we have a square, which is a special type of rectangle. It's it inherits and calls the constructor of its parent. It's a rectangle with equal sides. And now to important and what we will work with. So the abstract methods and classes. Abstract method is a method which is defined in the parent class, but it's not implemented. So in the sense that this is, if a child inherits everything, so this is a debt, like the parent has a debt which is inherited by a child and has to be paid later. This just defines, for example, what method can, what interface this class has. And if there are abstract methods in the class, then it's impossible to create an object of this class. You cannot instantiate it. This can be seen here in Python, for example. This shape class is abstract because it has abstract method, area, and we cannot calculate area for like an abstract shape. This means that any child class, if it wants to be real, not abstract, it must implement this area, like this rectangle. It re-implements this area method. And yes, the child must implement the abstract method, otherwise it will be abstract too. And these classes are like a declaration of our intention. We can define some function or some manipulation with the abstract class, like we have a list of shapes here, and we don't care which shapes they are. We just know that they have method area, and we can calculate the total area. We can do anything which you can do with a shape, regardless of which individual implementation it is. So yes, the user of this interface doesn't need to know about the implementation. And this is how Jant is built. And yes, we will also need to see a little bit in the C++. So the main difference for us as users, as viewers of the Jant class reference is that abstract functions are marked as virtual and equal 0. Equal 0 means there is no implementation. And just a virtual function in C++ is a function which can be re-implemented in the child class. So, yes. So this is a purely virtual or abstract function. And this makes a class shape abstract class. And this is just a virtual implementation. So yes, just virtual can be redefined. Virtual equals 0. Abstract must be redefined. So when we look on the Jant4 classes, we will see they have special notations. Every class starts with G4, then it goes like something. If there is V, then this means virtual or abstract class. It must be inherited to use. If it has name user, then it's intended for us to re-implement. It should be inherited by user. It is V user something, then it must be implemented by user. So this is just a notation. Okay, last point on this, and then we get to Jant. In many places you will find this singleton. So they really love this singleton. Singleton is a design pattern, so it's a way, let's say, to solve a problem. A problem of accessing one instance. So for example, you need to have like database, and you cannot have two instances of them. It should be only one. It should always point to the one and only. So it's defined with this method getInstance, which always returns the instance of this class. So you don't have to I don't know, it's like a president. There's only one president, and you don't have to specify, and you get the instance. Okay, so in one place you get this, you address the class, one and only database, getInstance, and you get this instance. And in the other place you have a pointer to exactly the same instance, and they have synchronized the data. And Jant4 also uses this pattern extensively. Jant4 is full of manager classes. For one worker class, there is a dozen of managers, and each manager is singleton. So you have to address them. But very confusingly, they have this getInstance method has different names in Jant, so you never guess. So one for run manager, you have this get run manager. For NIST database, you get this instance, and other classes have other methods too. So we just know that there can be different names, but this is all the singleton. So singleton means that it can be only one, and you can access it from everywhere. Actually, so this is basically, it's a global variable in a fancy dress. So sometimes it's considered bad practice, but it's there everywhere. Okay, so object is attributes plus methods in one place, and it's a convenient thing. Abstract class is a declaration of interface, so all the methods through which the object can be interacted, and we can interact with all its children using this interface. You can inherit from abstract class and implement the abstract methods, and you have to implement abstract methods if you want to make something real. And creating classes is free, and inheriting is necessary for Jant, unfortunately. Okay, so now we're getting to the Jant. And it's usually people start working with Jant opening the standard Jant examples. They have a lot of examples, different type of complexity, more and more advanced. But I think it's useful to try to build from scratch. You have nothing. You want to run a simulation. Otherwise, starting with example means you get to copy this example and modify it all the time. And so the main manager, it's called G4 Run Manager. We can create it, but as you remember, it's a singleton. It means that you cannot create it twice. And this means, in our case, that if you try to create it twice, that this will crash because it initialized the run manager kernel and other managers and so on and so on. So be careful. Or use the get run manager method. So it needs basically 3 steps. It needs to be created or obtained somehow. Then you call initialize when it performs all the initialization, and then you run this beam on, which starts simulation. And you pass a number of events, and then you're done. This is a skeleton. This is how it works. Of course, if you try to run it, the Jant will complain because you cannot make the tracking of particles in matter if you didn't define the particles or matter or physics. So we need to pass user-defined components. To understand which one, we can look at the class reference. So this is our G4 Run Manager. This is how the class reference looks like. It shows the inheritance diagrams. So this G4 Run Manager, you see it doesn't have letter V. Then it means it's not abstract class, but still there are a lot of other run managers inheriting from it. We will not consider them. And then there's a list of methods. List is very big, very big. We already know beam on and initialize. We try to not get lost in this. We remember that we are users, and the method should have name user in it. So going back, if we just write down all the methods which have this user in its name, we get this stuff. So several set user initialization and set user action. And these methods receive different objects. And you see some of them go with this V, some without this V, but all these are user something. So I remind that V means that this is abstract class. In our case, for the minimal example, we need, as I said, we need three things. We need particles, we need geometry, the medium, and we need physics, so the processes which happen with them. So these are these three guys. So user detector construction, user physics list, and user primary generator action. And this is example how you pass them to our run manager. So physics definition is in this physics list. It defines what particles and processes are used. Then we have the geometry definition with this class detector construction, and primary generator action. You see that two first we passed as initialization and the last one as an action. We will have a look at them soon. How do we create them? So these are all abstract classes, G for user detector construction. That means that to create such an object, we need to inherit, we need to create a child class which implements everything that should be implemented in this class. So yes, it's like to run a simplest example, you need to define at least two classes. By the way, you can start by opening the examples which were provided. Okay, we can get to it later. First of all, I will walk you through this, but then we will have to run. We'll have to try it, and we'll have some practice. So detector construction. We can look again at the class index, but anyway, the main thing here, the only abstract method in this class is this construct. A construct method which must return the physical volume. There's a lot of going on in here. Defining the detector in Jant is process in several steps. So the geometry is composed of shape, material, and also it's composed of inner hierarchy. So you can have one shape and you have another shape in it, and you have several shapes inside, and this is all hierarchical. This is the simplest example. First, we define the solid. Solid is object that defines a shape. In this case, it's a box, but it can be shaped. There are lots of solids. Let's also have a look at this link. This is a Jant documentation, and it lists a lot of predefined solids. So you see the cylindrical, conical sections, parallelepiped, trapezoid, etc. And these are all available for us depending on our task. It's also possible to define geometry using triangles. etc. But for this simplest example, we use box. It's a big box, 1 by 1 by 5 kilometers. Then we need to define its material. We are using again the singleton. This is NIST Manager. It's a database of materials and elements used in Jant. So we don't have to define everything from scratch. We just find or build material G for water. So there's also a list of available materials and elements. And it's also available in official documentation. We use water. Then we need to combine the shape and material. This is another class, G for logical volume. We combine this box with water and add the name, world. And finally, from this logical volume, we need a physical volume. Physical volume is a logical volume placed somewhere. So it needs coordinates. So this is done, in this example, it's done with this placement, G4 PV placement. We can define rotation matrix, translation matrix. We can define some mother logical volume if we want to make a nesting geometry hierarchy, etc. But for the world volume, we don't have any mother. So this is the topmost volume. Okay, and finally we return the physical volume. The rotation and translation, so in this case they're 0, but whenever you build the hierarchical geometry, you will need to define this position. So these are define the placement in the reference frame of the mother volume. And also you can make many placements of the same logical volume, so you can define some part of your detector or part of your geometry and make an array of them, and this is how it's usually done. Okay, then we have we need to define the particle, the primary particles, which will be traveling in this geometry. This is done by the primary generator action. It's action, not the initialization, because it needs to be executed at the beginning of every event. Every event should have a new, actually, primary vertex. So G4 event is a container with all the stuff belonging to event. It has a primary vertex, one or many, which contains one or many primary particles coming from this vertex, and each primary particle contains the particle definition and the energy, momentum, etc. So for primary generator action, we have this necessary method, generate primaries, which will fill the event. And actually, you just need to put the primary vertex in the event. You can do this by hand, calling the appropriate methods, event, set primary vertex, you create the primary vertex, you fill it with particles, etc. But usually it's done with usage of some other classes, like this particle gun. In the constructor, we define the particle gun, set the particle to be muon, and set to this particle gun, we set that we want this particle, energy, here it's 10 GeV, direction of momentum, and particle position. Okay, so this particle gun is one of the implementation of primary generator. It's not to be confused with primary generator action. Primary generator is a thing which should be used inside primary generator action, but it's not necessary. You can do it by yourself, but yes, this is how it works in Jant. And for the physics list defines everything that happens during the tracking. And it's governed by this process classes. Each process acts, well, the simulation happens in steps. And during each step, the process is applied to the current particle, to the current track. It has a way to check if it's applicable to this particle. Then it has three methods. It can do something along the step, it can do something after the step, and it can do something if the step is at rest. So, and for each of this, it can propose this object particle change. So as you can see, everything is object, and it's a different object. You have to look into the class reference to understand what it holds, and yes, everything is convolved. But the idea is like this. So this particle change proposes the change to the track properties, so we may lose the energy, change direction, etc. Also, it contains the secondary particles which can be generated on this step. Okay, and there are lots of these processes defined in Jant, and we don't have to program them from scratch. They fall into these 7 categories and grouped in the physics lists. Each physics list defines the particles which are used, which can happen in our simulation, and the processes which work with them. So here we use the standard, one of the standard physics lists. Yes, sorry. The model of physics lists are the physics list which have processes grouped by these groups, and you can add or remove or modify, replace a physics group of these processes in modular list. And then there are these reference physics lists pre-made by Jant collaboration. They have their recommended use cases, so we will use this default, recommended default for astrophysics, accelerator, etc. applications. So they have the recommendations. So if we run the minimal example, so those of you who have notebooks, who have downloaded the examples may try to run it. By the way, how many of you can have the equipment? Okay, cool.
May I ask a question?
Yes, sure.
What does mean less in this?
Okay. It's just a utility to watch the output, to scroll through the output. Because when you run, Jant just produces a lot of output. So.
Yeah, I see.
Like what? Pum, pum, pum. So we run example 0, and we have a lot of stuff written, defining our physics, electromagnetic parameters, etc. Yes, it's because of the less, it's not showing everything. It shows all the processes defined for the particles. Okay, so this is all the part of initialization. Then we have this run 0 starts, run terminated, run summary. We have 10 events, but yeah, nothing happened. This is boring. We wasted our computing time for nothing. So simulation finished. We need to add more action. So the actions, user actions, are the objects which can be used to interact with the simulation chain. So we've seen that there's initialization. This is object with methods which are ran when the manager initialize is called. So this on the initialization stage, like physics list and detector construction. Then the action is object which is called automatically during the simulation after we call the beam on. We've seen the primary generator action, but there are more actions. So if we look again at the list of possible methods with the name user for the run manager, we can see other stuff. So we have this, yes, run action, event action, stacking action, tracking, and stepping action. And also this one user action initialization. We'll talk about it later. And all these actions, so this is where Jant works like a framework. You implement an action and it gets called by the run manager at a specific moment. I'll try to be short on this. So run action has methods which are called at the beginning of the run, at the end of the run, and the run is just when you call this beam on function. So it's whatever you define. You want 1,000 events, then it's one run with 1,000 events. Then you call it a second time, it's a run number 2. You can also modify this G4 run container class if you want, but we will not do this. Event action has also is called at the beginning of each event, before processing event and after processing event. So this in these simple implementations, I just put the print functions and that's all. But we will see when these guys are called. But you can do much more. One warning that this event container is a volatile container. So after the event is finished, it is erased. So if you didn't save the data, you don't get anything from the event. That's what happened with us. I mean, when we ran these 10 events. Tracking action is called when new track starts to be processed and when it finished. So we can get initial or final information about the track, and also we can modify the track somehow. For example, we can kill it if we set this track, this G4 track container. We can set its status to stop and kill. Under some conditions, if we don't like it, we can do this. Okay, so there's one more action, stacking action. And this requires a little bit of explanation. So this is how it works in Jant. These decks are, so each bar is a track, okay? A primary generator puts primary vertex into the event and it contains the primary tracks. Then these primary tracks are taken into the list of the new particles, and each of these new particles has to be classified. We have to decide what we should do with it. That's where this stacking action goes. It classifies a new track and it can put it into one of the 4 stacks. So the stacks are like literal stacks, like a deck of cards, in a sense that you put something on top of it and you take it last in, first output. So there is an urgent stack which will be taken for the tracking. This is how everything happens. We have these processes, they modify our track, they produce secondary particles, etc., and produce steps. We can classify it as waiting, so it just fills this stack, and this stack will be taken when this urgent stack is empty. Then there is this postpone. It means to postpone to the next event. So we can just make our events like talk to each other by postponing particles. Yes?
How does this thing postpone events to the next, or postpone tracks for the next events if we have only one event at one time? It saves it?
Yes,
So the track isn't in this event?
Yes. So all these stacks are not in the event, they're in the manager and at the end of the event. So these are empty, but this is kept. And this is, everything from this stack will be passed to the new particles of the next event.
And the scheme of this thing, well, the conditions where which track should go to which...
You mean this stack in action? Yeah, this is user-defined, yes. Yes, you can do whatever you want. And yes, the last stack is the trash can. You can kill the track at the stacking moment. Okay, so this is this. Sorry. I lost it. Yes, sorry, they got mixed. This is a stacking action. We classify the new track. Okay, already. And the default result is urgent. Okay, and finally we get this step in action, and it just gets called on every simulation step and contains a lot of information. Actually, this step object, it's a container. It holds the first point, the last point of the step, and all the information about the volumes which these points belong to, of the processes which created this step, of the energy deposition, and so on and so on. And all the secondaries which were produced at this step are also in here. So in this example, I just print this track information and step length and energy loss obtained like this. So, but beware, this function is called on each step, and there are lots of steps, and this can and will impact performance. Actually, since this is a Python function, just by defining an empty step in action, you get your jump 2 times slower than without it. Okay, and adding action to the run manager, we use this set user actions, which can just pass them here. It can be done before or after they initialize, and you can have only one action of each type. So if you pass another run or event action, so the previous one will be overridden. Yes, there is another way to make a class of like action initialization, which does all the same, but in the build method, and this will set, this is initialization, so this must be called before manager initialize is called. Okay, let's just run with actions. Spoiler. Okay, we get all the same output, but then we get information about each step. let's look at it here in some detail. So this is just, this shows a scheme of when these actions are called, and we get some information. So we starting event, then we add the primary particle to the stack. You see this muon with no parent is identified as urgent, so it will be tracked. Then this muon starts being tracked, and this is a tracking action reporting. And then we have a lot of steps. We have energy loss, we have some millimeters of distance, and our kinetic energy is decreasing. That's normal. After some thousands of steps, we finally get our muon to the kinetic energy of 0. And you see the last step is has 0 length because it's a process at rest, and the step is in time. So it gets it decays or it gets captured. Then only after we finished tracking this muon, we are considering the secondary particles which were born in all these steps, all these processes. These are there are lots of delta electrons. They're processed here one by one in chronological order and added to the urgent stack. And finally, we have these products of the muon decay or muon capture. And this is anti-Nu, nu mu. And because this is a stack, it takes the last card from it. So last card is this nu mu, and it starts going downwards in chronological order. So you see ID 1351. It's the last which was added. And for neutrino, in our case, we have only one step, a very long step. It's because JANT doesn't, in JANT, neutrinos do not interact, and it just propagates them in one big step out of the volume. And yes, the next particles are taken in reverse chronological order because they are in the stack. Okay, so for some practice, I just wanted to suggest using these examples, using this template actions, just practice on getting the information from them. So no, the first one is not getting the information, but setting. It's to make our primary generator to have random energy. So how much time do I have? Is it 0 already? Yes, it's 1. Okay, then it's for later, or maybe for the break. Okay. So yes, basically you will have to modify the primary generator action and assign the random energy as the gun energy in the generate primaries method. Okay, then another possible task is to obtain the muon range in water. So this is we use a tracking action. We take the track at the beginning and at the end, and store its energy and difference of its positions and plot it. Okay. And finally, it would be nice to have a muon energy loss and compare it to the PDG. So this requires working with a step-in action, and we get the information from each step. And also, it would be cool to plot the energy loss for each separate process. You can get the process name from the step as well. Okay, so let's stop on this now.
Thank you for your lecture. My question is regarding to the Monte Carlo method. Is it a fast method, and how we know when it's safe to stop generating random values?
Well, you can define, you can estimate the uncertainty of this method. So this is an approximation of your integral value.
How the convergence increase with the number of points?
Well, I don't have a direct answer to this because.
Inversely proportional to square root.
Yeah, yes, but this depends on the way you sample.
Yes.
So you can get better than this. You can get worse if.
No, the low is always like that.
Yes,
The
yes.
coefficient is dependent.
Yeah, yes, yes.
Thank you for your answer.
Yeah.
Thanks for your lecture. In page 25, you mentioned you introduced the physics list. In G4, the default hadronic energy limit is 100 TeV. So how can we go beyond that? Should the CRMC a good choice or good option?
Yes, I suppose this is one of the good options. CRMC is a separate package which makes the interaction of higher energies, and this is it has interface to JANT as well. And yes, I think so.
Thank you for the lecture. I have a question about the garbage collector. So this conflict may occur if we but configure stepping action, or where it may occur?
Actually, it can occur. It can occur anywhere. So I encountered it in the primary generator when I create the vertex. And I create the primary particle, put it in the vertex, and I put the vertex in the event, and then pass it to JANT, and there's this double counting. There are ways to get around this. Well, the simple but a little bit ugly hack is to not allow Python to do the garbage collecting for these objects. So you just add them to some global list, which it has to keep in mind until the end. So this works. There are other Python bindings, G4 PPYY, and they have some special tools for declaring such objects which are not to be destroyed, not to be treated by Python garbage collector.
Thank you.
Yeah.
Thank you for an interesting lecture again. And could you please talk about uncertainties? What main sources of uncertainties of this Monte Carlo method, and what maximum
precision
with Monte Carlo corresponding to real detection?
I see. So, well, the main uncertainties, of course, are systematic uncertainties in the models. So it's defined by the models. I think hadronic models are the ones which are less known, or at least have the larger variation. So that's why we have different hadronic models. We have also another package. We have Fluka, which is closed source and has its own hadronic models and considered to be slightly better. In some steps we have how's it called, MCPN or something like this. So yeah, there are.
Experience. What the best correspondence between experiment and Monte Carlo?
Oh well, it depends on the task. It highly depends on the task. If you want, if you have like something simple like muon's range, then everything works very good.
From what I can see at the moment, it looks like the toolkit only implements the binary processes. Can it in principle implement triple processes like induced scattering or something like this?
So by binary processes, you mean when our particle interacts with the medium, and that's
one particle and the target and the interaction. What if you have one particle, another particle, and some background that actually defines the interaction, like induced scattering?
Oh, then this background can be part of your medium. So you define the process, and so in this this description, this is also a medium. But particles, these primary particles, they do not feel each other. They are treated separately, of course. Yes?
Thank you for the lecture. I have two questions. My first question is related to possible application of GN4 in astrophysics. As far as I understand, accretion disks are usually simulated using hydrodynamics or grid-based hydrodynamics. Could GN4 be used for any part of accretion disk modeling, for example, for particle transport or radiation processes?
Well, that's an interesting question. I don't think that this is within its limits application. So Gen4 usually doesn't consider any kind of gravitational effects at all. So you probably to some extent it can be made to do this, but I don't think that
I think gravitational effects it's not so important here. Just can you use a background from astrophysical simulations as a target for simulation of particle propagation?
Oh, okay. Yes, this then it should work depending on the energy range, of course. So that said about CRMC and energy limit.
Thank you. And my second question about how exactly you can using Monte Carlo methods for training an email model.
Well, you have coming back to the beginning. You have these nuisance parameters as we call them, but usually this is called Monte Carlo true. So this is not nuisance. This is something that you do not see. So for training, for example, for supervised learning, you can have this X goes as an observable, and nu goes as an how's it called, an answer. So the label, for example. So this provides you with the synthetic data which you can train, and with additional parameters which can be used for reconstruction, regression, etc. So you can get the value of the new one from X, for example. Yeah. Okay.
Thank you very much for your lecture. For the recent time, a lot of investigations are in the field of structured beams, which are not concerned with just momentum and such properties such as mass or charge of particles, but with some inner degrees of freedom, such as orbital momentum for vortex schemes. So maybe you know, if developers are interested in developing the GEON for this structured beam.
Well,
so maybe some libraries or packages are preparing to calculate or to simulate these beams directly without further проработки. Well, without further treatment and with counting the interference between the initial states of different plane waves in these structured beams.
well, I'm not sure about this. I don't think that. So again, as I said, each particle is considered as a separate particle and it doesn't interact with anything else. That said, you can define its initial state from the definition of this structured beam, but when it comes to the propagation, I don't think that it's yeah.
Okay, it's just
I'm not familiar with it.
Frontier of the physics, so of course it's cannot have clear answer. Thank you.
This is beyond my knowledge.